You call it, or she'll call it, and then they say they reimburse the card.
Okay, cool.
And the service guy's coming.
Nice. Yeah. All that. Okay, well, that's good.
Here, I'll try to.
I don't.
I'm also are you sure that it's because I remember that I didn't know if I could be able to react to this. Okay, yeah. So I did work and I was currently working on stuff. Or haven't used it, I don't know, the last 2 years. Yeah, there was stuff there. It's just a little bit of like mostly that fits so probably all the time. I'm gonna find it in 10 seconds.
How many times did you Okay, but I also I woke up and turned it on. No. No, but you no. There's no gas in it. If there's no turn on, I'll be like, mine makes this like 3:35. I think it's an answer. I did that. Then this is not so good.
Yeah, it's just
Run
my
my
dad
sister's
asked me
house,
yesterday.
and can I do it? 5 seconds. I just
I can't get a jailbreak.
Very mildly. Yeah, the camera.
I did. It's not my fault. It's a viable place.
I don't have my other.
Yeah, I'm offended that I forgot.
And then there was like this. If you were
All right, first problem is on the board for review. And then let me know if things look weird with your grades or anything. I think I need to double check some totals. Some people are telling me the quizzes might still be wrong. But yeah, check your grades, make sure they are up to date, so they should be complete. I think there's a few straggling assignments from a few people, but for the most part, they should be complete. And then I'll also try to hand back everything today. Oh yeah, I'll post it once. It was being buggy. All right, who wants to put this on the board or at least start it for us?
Oh, that was close.
You caught it, you saved her. Yeah, so walk us through and then I'll try to copy you.
So I started getting the moles first. That was my first step. So I believe that 63.546 grams per mole. And then I just divided the moles.
I think that is just for copper, but
Is
yeah.
that just for copper?
Yeah.
But I think that's fine.
Yeah, because I don't think we should actually care about it.
That must have been from my notes then, yeah. Just erase the sulfate would be fine. So I got about 2.4 times 10 to the -4 moles. And then what I recognized was that with this compound, this copper sulfate, that there was 2 moles of electrons because of that difference in 2 charge. And then I used that number from our textbook. We have coulombs of charge per mole of electrons. And I multiplied that by 2 times this number because there's 2 moles of electrons. I got about 45.55 coulombs. And I believe it was 10 minutes.
Yep.
So I took that amount of charge and multiplied it by 1/600 seconds. And coulombs over second is amperes, so I got about 0.076 amperes.
So that sounds good to me. I'm just catching up to you.
That seems good, or? For you?
5 coulombs.
Sorry, my handwriting's kind of small.
I also have that handwriting, so. So did we have questions on that? Do we need to go over any part? Do we all follow questions on that? What did you try, or did you use another constant, or?
Well, I first got
or divide, yeah.
Or divide it, yeah. And then I multiply it by 2 moles ratio.
Yeah, that should still be okay, because we did that down there.
So then I multiplied that by the rate constant.
Because I feel like you did the same thing, so 964. Because then you would have done times 2 times. Because that, I might.
I used the full value in the calculator, so I got slightly different than that. I got the 45.55.
Yeah.
Not using the rounded rules.
So, but somewhere around like 45, 46.
Okay, and then you divide that by 9.
Yeah.
Okay, I think I was step by do that. Okay, thank you.
Cool. Other questions? Does that make sense? And then, right, we need to divide by seconds since our amp is defined as coulombs per second, so that's our current measurement. All right, let's try another one. And so let's say I want to build a galvanic cell. So if I have zinc, so either zinc 2+ to zinc and a tin system, so which is my anode? And then go ahead and sketch the, sketch a galvanic cell diagram. Someone put our sketch on the board for us. No one wants to sketch our cells somewhere. We could put on the far board too. Could team it. Madden, how does your galvanic cell look?
Not good.
We could help you. You want to put it up on the board? Anybody want to try? All right, somebody help me out. I'll put it up, but you guys are going to walk me through. So what do we need in our galvanic cell?
We need
So 2 containers. So I'll draw my little beakers. All right. And then it does ask us, so maybe we should start with that. So which one is our anode? So what happens at the anode? That could help us too. So oxidation. Right, so something needs to lose electrons. So what metal is more favorable for that?
Zinc,
So zinc, so how did you know that?
because it has a lower oxidation potential.
I guess it depends what we're looking at.
Yeah, yeah, it's so lower.
So it's what? More negative?
Yeah, it's like a larger negative number compared to 10.
So more negative on our reduction potential. And then these are always kind of confusing. You can tell since zinc is higher, but right, you're really thinking of the flipped reaction because zinc is going to be losing those electrons, so it's really positive, right, 76 volts for the reaction we're interested in, versus, let me see if I can find the tin I'm using, a very detailed one. Oh, there's tin. And so tin, right, is less negative, but again, you're thinking of the opposite reaction, so it would also be, right, lower, so less positive in the forward direction. So does that make sense on selecting the anode? All right, good. So we selected our anode then, so our zinc.
That's the most negative.
Yeah, so the most negative, but based off of this chart, right, which is kind of going in the wrong direction. So yeah, it's more negative.
So is this a chart of reductions?
Yeah, so I'm just looking at standard reduction potentials.
So what would be the compound with the higher oxidation potential but lower reduction potential?
Yeah,
Okay.
yeah, since this is a reduction potential. So all these at the top, right, are good reducing agents. They're getting oxidized, though, primarily. We don't see lithium doing that. Obviously, we could force it, right? And we can think about mining lithium. Great presentation on that, right? So right after they get it all out, mine it with all the water apparently, then of course you have to do some sort of electrochemical reduction, so. All right, so now what do I need to draw? So I have my jars. What do I put in there? Salt bridge. So yeah, don't forget your salt bridge. So we just need some sort of ion channel. So we can label this salt bridge. And in this case, so another thing we'll point out for this example, so we are going right metal to metal. So that's not always the case, but that means we can draw right our piece of metal. So I'll put our anode side with zinc, and that means we need zinc 2+ floating around. Then our tin side, so a tin metal, tin 2+ floating around. What else do we need? So some sort of wire circuit. And then which way do the electrons flow? Oh, I haven't updated it. So where do they flow?
Towards the tin.
So towards the tin, right? So from the anode to the cathode. So electron flow. Let's see.
Could you remind me what the exact purpose of the salt bridge was again?
Just so you have flow of ions and to kind of complete the circuit, so you have to have still ions flowing. And then, so what if we were given like another system? So let's say we were looking at a tin 3+ to tin 2+ system instead. So we'd replaced our tin with titanium, So titanium. So looking at titanium 3+ to 2+. What's the difference? What do you have to use if you have this system? What did you say? Not hydrogen, but something, I think you're, not a battery. But right, identify the problem. So what's different, right, from this system to this system?
They're the same metal and different oxidation states.
Yeah, except because this is the same metal, different oxidation states, but what's the difference?
Wait, are you talking charge? In the solution, ion is different than what?
Yeah, so basically, right, let's say we're drawing an analogous one. So we're doing, let's just pretend now we're doing zinc titanium, but we're using this weird titanium 3+ to 2+.
Are we talking mathematically or just the structure itself?
Structure, yeah. So yeah, obviously they have different reduction potentials, but what else is different? Because what do we do for the zinc and the tin one? Right, we drew a little piece of metal, right? So they went to their metal form. Yeah, so what happens when it's ion and ion? What do we need?
Don't we need like a catalyst?
Yeah, so we need a surface basically, and then do we remember what that surface was typically? So sometimes platinum or the glassy carbon, so like glassy carbon. So yeah, we need some sort of surface, exactly. So right, we need a place for the electrons to exchange. So that would be the only difference, is that we have to include some sort of glassy carbon electrode. So glassy carbon is just kind of like graphite that's polished. And then in solution, you can have titanium 3+, titanium 2+, both floating around, but yeah, your solid piece is a glassy carbon. That's the only difference. And so same thing, right, electron movement, salt bridge, all that's the same. And again, so this would be any system that doesn't have, right, a metal piece.
So it could be platinum, or
Yeah, so so platinum or carbon would be the two typical ones.
I'm assuming likely just something that's not going to react much.
Right, yeah, so kind of an inert surface, yeah, just for the exchange. Yeah, so I'll just give, right, another example where we might need a glassy carbon electrode. And it could be anything, but, right, like our sulfates, so the S2O8 process, plus 2 electrons to give us the sulfate. So, right, that's just another example, right? Ions in solution, they need somewhere to go. Oops, that was supposed to be 2 minus. Etc., right? So this is not exhaustive, could be any other metals going from different oxidation states. All right. Questions on this? Do we feel okay about this one? I'll share the notes in a second. All right, let's try our next problem. So metal X has a neutral configuration. Of argon 4s1, 3d7. And so let's say we're looking at this compound, so XY6, 2+ here, and Y is a neutral strong field ligand. So see if you can determine the coordination number, shape, and then high spin, low spin. And then whether it's diamagnetic or paramagnetic. Forest 137. And so that means, right, when it's a metal. Bless you. how are your answers looking for this one? And so what were they trying to tell us about this metal? So they told us its neutral configuration. So how many D metals would it have total then? 8, right? So remember that we just effectively say that anything in the S, whether it's 1, whether it's 2, right, they just act as all D electrons. So it's D8, at least, right, if it's 0 oxidation state. Again, this is, right, as a metal now in a compound. And so then it has this 2+ charge on it, though, and it says that our Y is a neutral strong field ligand. So now what's our D count on our compound? 6. So I hear D6 from everybody. All right, so now we're at D6. Looking good. So what do we say about our strong field ligands? What do those compounds tend to be? What does that mean if it's strong field? So strong field, low spin. So right, they usually have a higher energy gap if they're strong field. And so I'll just say that. So strong field. Equals greater octahedral splitting. And I refrained from doing any energy calculations. And so now we have a greater splitting. So probably low spin. So then we fill in our 6 electrons. So 1, 2, 3, 4, 5, 6. So D6, low spin. And then diamagnetic, paramagnetic. So diamagnetic, no unpaired electrons. Sweet. Oh, so the shape mainly just depends on how many you have. So if it's 6, you just normally assume it's octahedral. And then I was going to point out, so I did kind of make a blunder in one of our quizzes, but nobody caught on. So we can kind of talk about this one. And so the question I had asked, and this was at least labeled quiz 7, I think I got off somewhere in our weeks. And it was question 2, and it asked how many unpaired electrons, and I still have some quizzes that I need to hand out. So it says how many unpaired electrons in this ruthenium tetracarbonyl compound, 2+. And so most people, so if we look at ruthenium, so right, it's under D8. I should pull up a periodic table. So ruthenium, right, it's D8 here, so we just treat it as a D8. And then I put 2+, COs are neutral. So when I wrote this question, or wherever, if I stole it, I don't know if I stole it or wrote it, you know, it comes out D6. And most people picked 0 as the unpaired electrons, except I later realized I made a mistake. So going back to now your geometry question, so something that has 4 things attached to it can only be in 2 different configurations, right? So it could either be square planar or it's going to be tetrahedral. And then for our purposes, right, we didn't really go over the square planar splitting diagram. And then if you do the tetrahedral one, so the tetrahedral, you fill it in, so 1, 2, 3, 4, 5, 6, and it probably, the correct answer should have been 2 unpaired electrons, but that wasn't an answer choice, and nobody drew it out and like questioned me about it. So yeah, the answer was 0 then, but so that was my blunder. I'll have to fix that. But then following up to your question, well, how do we know the shape? Well, we still don't really know the shape from this information, right? So we have to pick between square planar and tetrahedral. But then that's where the isomers come into play. So then tetrahedral has to have optical isomers, or has the potential to, right, if there's a substitution. And so that's the difference, is that if you have, right, different ligands on here, so in this case that wouldn't work since, right, there's no optical isomers. So you'd have to do something else to determine, so then it would turn into a symmetry argument, blah, blah, blah. But that's beyond the scope of this course. So basically, to answer your question in this class, if you have, you know, something with 6 ligands attached to it, right, then you usually assume that it's octahedral. And then if it's 4, right, you have to distinguish between the square planar and tetrahedral. But we're not going to go, I'm not going to make you do square planar splitting diagrams. So the question would probably say something about optical isomers or not.
Why is there 2 on the bottom instead of 2?
Oh, that's the tetrahedral splitting diagram. It's flipped of the octahedral. So yeah, I don't want to get into it, but yeah, basically they pair with completely opposite orbitals. But so that's why it's a flipped diagram. But yeah, that was my mistake on the quiz. No, we just don't want to get into MO orbital theory, and then everybody will be bored. I'll be really excited. And then the only other thing on the quiz that I wanted to point out was the cis and trans question. And so a lot of people got that confused. So I think, so that it was the same quiz, so which of the following have cis and trans? And so the so the wrong answer that people selected a lot of the times was this cobalt water. So it has, right, 3 waters, 3 chlorines, except what isomers do they make when you have half and half? Do we remember the name? We can go over it again.
It was kind of like system trains, but it wasn't quite.
So it's FAC and MER. So remember, these have FAC and MER, or, right, they've had those names of like cis, trans, and something else.
Yeah.
But this is the only one with true trans and cis isomers, right? Because it has 2 substituents, and this was kind of confusing because you had this outer sphere chlorine that could have thrown off some people. So then you're just looking at this cobalt coordinated to 6 things, and then we could draw out the cis and trans isomers. So the only options when you have 2 different substituents is we can have, right, the trans isomers where they're directly across, or the cis where they're next to one another. So trans and then the cis, they're next to, so different axes. And again, you would be able to tell these apart using spectroscopic techniques. So like IR, they'd probably have different stretching frequencies, but you would get all into that later. So trans versus cis. So those two isomers versus, and I could draw the FAC and MER ones again. So remember, the FAC is on one face. So X. X and X. You can rotate it. Oops. So there's the FAC. And then MER is where they're like a cross. And then next to, so MER, and then remember your book calls this trans cis, but it needs both of those. And then the FAC is cis cis. But again, only your book, well, I'm sure other places use it, but I've really only seen your book use that terminology. Otherwise, I've just seen the FAC and MER. All right, I guess that's a good spot for a little break. I'll keep handing back stuff, and then we'll look at some more polymers and a little bit of radioactivity. Try to hand back all your quizzes. Sorry, you two are still going to write Oregon cave essays, right? Okay, yeah, just whatever, because I was both holding off on both of you because you both haven't given me essays, so I was just double checking.
I have a question, and I feel like I've missed a couple of random Thursdays, but I can't tell which quizzes I'm missing, but I feel like I'm really missing.
Okay, I will look through them and then I can you hang out after class?
Yeah, I should be able to.
Okay, and then I'll get into you.
I'm having some trouble accessing this journal article. Like, all the other ones have worked just fine except this one.
Oh, I think I posted that one already.
Oh.
Nope, it's on the front page.
Thank you.
I couldn't find any old like newspaper history purpose, so that is from scratch.
Okay.
Not the best work ever. I'm just gonna put that out.
I'll keep that in mind since, I mean, I know you joined in the third quarter.
We're okay here today.
I haven't, this is really interesting.
I'm so far behind that blue register. Because I have, well, I already have physics.
And I was just like,
And algebra and this class. And I don't know anything about that, even if
because
this
of
was
when you
not.
get and then it's gonna be like really sad.
I wanna see the graph of your grades. Well, I mean, yeah.
I have edits.
Imagine getting it.
This one,
And get everything on
Okay,
one.
I think that's what we're doing. Okay, cool. I gathered. Okay.
You're making me cry.
Oh, like a blank one?
Yeah.
I think I have one in my office.
You get two, actually.
Okay.
Well, it did pretty much everything for us. It's whatever he hasn't done. There are 2 questions for me. So like. But only that.
The physics review go well after this week. What was the rest like? Was it like the most probable velocity? Oh, those are super easy. Yeah, those are like, I think, the hardest for this like whole week so far. It's like very
Me and my friends do PowerPoint nights, we make a PowerPoint about something, and
Okay.
there's no change.
Okay.
It just popped up on my screen. I was trying to look at the notes.
That's a good idea for starting.
To not study.
Yeah, true. Yeah. You still have an issue with that one?
He's not there.
I just heard you two talking about the one thing and never heard anything else about it.
Yeah, because that was the.
Yeah, that was it. No, cool. Sweet.
Yes, I did.
Oh, there was, I was told not to talk about it. That's why I haven't talked about it. Long story short, there was a guy in my class. He did some very bad comments. Is the assumption. I think that afterwards, our professor, instead of acknowledging, I'm sorry, I just had to in our classroom. I felt that, he's just here for the term, he's a sub.
Why?
It's just like, literally like this the whole time.
So I'm testing. It's like
I see, I planted to ask you.
No, it's, I mean, it's good.
well, it's not so much what's
Okay, I don't know.
Well, so far, I haven't read,
I didn't want to just be out and
Carbon
like,
has
do those stuff,
and that's another thing.
but like, okay.
Because that's why we, that's why we're.
I don't want to, I have wood, I can get wood from my
yeah,
camper.
he's crazy.
I think we just.
Wait,
Yeah, and I mean, yeah, like I said, when I asked her, like, is this place like that, they just, I can look up and look up, be like, I don't know how.
yeah,
That, I was planning on.
Yeah, I was planning on asking her that, and then I had some stuff I couldn't I'll tell you about.
Well, I just, well, because I think Francis is not always here, so I'm wondering, and then I forgot that we don't have it. Like, I knew it, but it wasn't like, I'm consciously there, so yeah.
I mean, you could bug Marissa for review stuff during that time, she probably won't cover it. Yeah.
Like, that was also a problem, I was not here.
I'm just saying, you know.
Yeah.
so
At
it
least
starts
that's how
off
it's
in an
done.
adapt. Oh, that's Francesca, but it doesn't even have her face, it's just her mind.
Our books.
Yeah, well, we have to get some chats.
I have to go to the right after.
It's like, I'm gonna have taken that for this meeting.
Yeah, I
And then she goes and
Yeah.
it's just this thing like, I think you have a good answer. No.
Say a week, this week.
Tomorrow.
I will wait. It's not his
I had
fault.
an appointment 3 hours.
No, it's over the phone.
Today,
They are the
got a coach driver. Then I have my dentist appointment tomorrow that's been putting me on.
Well, they only have 4.
It's hard to get those, yeah, it's hard to get
They
those.
have
Yeah,
these,
and then
like,
on Thursday, I don't think she has the appointments, but I have final presentation. Then Caitlin and I need to drive to, my city. And I have tax. You're just busy all the time.
Yeah, I just,
But it's okay.
I just came before to be over. And then we get to-
Impossible, no one will ever.
You should have set one up.
And this password, like insanely long.
It's California.
I have a great excuse.
They're like
I failed music exams. I have a fantastic excuse.
Yeah, 4.00.
Except short of being critically.
And then you can start working on this problem. Hopefully I made it large enough to read.
Yeah, you get the first beats. Is that 1.87 multiplied by 10 to the negative 2?
10 to the positive 2. So how's this problem going? What? You're kind of lost.
So it's all the organic chemistry in the brain.
Yeah, we'll switch back to OChem after this.
Okay, you get some brain rot.
But, well, what equations do we have? Let's start with that.
We need to use our half-life expression from the rate law, right?
Yeah, so which ones are you thinking of?
I was thinking at first of the half-life expression of T to the subscript 1/2 equals 0.693 over K. But then I was also looking at the integrated rate law, and I thought we maybe need to use that. The ln of A subscript T over AO equals negative KT.
So that's a good start, and I think we'll need both of them, actually. And so what can we start plugging in? What do we want to solve?
Plug in the half-life to find our K.
All right, so let's do that first. So that's at least a good, easy step here. So now we just divide, so let me just clear this, 0.693 divided by our half-life, so 5,730. And that might be an approximation, I'm not sure. That's just the value I have. So then K is 1.2 times 10 to the negative fourth. All right, so then you said let's use this equation as well. And so think about what it's kind of telling us, right? So it's basically saying, and I think a good way to think about this is think about when we generated our little barium-137, right, isotope, and then we put it directly under the detector and it started decreasing. So that's basically what's happening here. So we're comparing it to a current artifact, that's full of the appropriate amount of C14 that we expect at our isotopic abundance, and it has 400 disintegrations in a 24-hour period. And so we can put that number on bottom, since that's our original, or kind of 0 time point. So we're saying, right, this is now. And then, yeah, so it's A of 0, or like your starting position. So that's what that A0 means. And then, right, we're just comparing it. So what if we had gone into that, cesium-barium decay experiment, but we entered it like 10 minutes, right? That's basically what we're saying, is we only saw a small portion compared to the full decay. What's the T then? What's the time period difference between them? So then we can plug in, right, our 1.87 times 10 to the second for our T, since that's what we're trying to solve. And 0 is our original. Now we have natural log of 1.87 times 10 to the 2 over 4.00 times 10 to the 2 equals negative KT. But we can substitute in our K. This is looking better and better. And so now it looks like we're just left with T as our variable. And then keep in mind our K does have a unit of years, so let's plug that in. So 187 over 400. And divided by our K, or negative K. Yeah, so you get years. And then I get like 6,300 years roughly.
6,287.
Ah, So I'll just round to like 6,300.
Yeah, if we were going to use significant figures, I think that correct it.
Yeah, I should give it another sig fig, but I'll just leave it like that since, yeah, so somewhere around that range depending on your K. Questions on that one? Oh, I forgot to mention, so another thing that came up on the aspirin synthesis, so everything looked really good. Most people did really good on that one. But then for some reason, I noticed this mistake consistently. And it was on the back page, the condensation reaction. And it was our acid, so our carboxylic acid plus ethanol. And so for some reason, I noticed that a lot of people made the connection over here at the carbon, so that was backwards. But remember, right, the action always starts at the oxygen, so the oxygen's going to attack. This leaves, but then that means that your connection is with the oxygen of the alcohol. And I probably should have picked a different color. I'll highlight it, right? So then this is our alcohol over here, starting at the oxygen. So that was just a really common mistake, so I'm not sure what happened there at the end. Everybody flipped it, but just, again, always think about where it's actually attacking, connecting from, so you make that correct connection. And so we'll keep on the train of polymers.
Sorry, so you said that it attacks that carbon that's double bonded to the oxygen?
Yeah.
And why exactly is that the case, or is?
Well, it goes back to, this is susceptible to electrophilic attack since,
Okay.
right, you have the resonance structure,
Yeah.
so that can go. So if we were to draw this, right, so, oops, sorry. So, right, electrons go up to the oxygen, and then you're left with our weird intermediate. There's our ethanol attached. And at this point, it still has the H, and then probably some sort of proton transfer, or if we want to, you know, like I said, depending on your future professor, they'll either be really anal about this or not. But some sort of proton transfer to go over here, reform the double bond. That's where the water leaves. But again, the important part is, oh, that's our alcohol connection, and it connects at the oxygen.
Thank you.
Yeah. So then part of your exam will be that you look at a polymer, and you might have to determine what the monomers might be. And so let's look at this example, if I can do it. And so I'm drawing out the polymer Nomex. So I'm just trying to draw out the monomer for you, and then y'all can draw out the polymers. And kind of look at the structure, right? Where do you think it has connection points? Oh, I don't know why I drew a double bond over here. Would anyone want to draw the monomers on the board or anything?
Sure, I can do that.
All right, go for it. And then, I don't know where our one marker went. I have more.
Okay, so I found that there are two monomers. The first one is the benzene ring with some amine groups attached. And the other one is the benzene ring with some carboxylic acid groups attached to it. And then they kind of add at this group by a hydrolysis reaction. Oh wait, no, by a condensation reaction.
Yeah,
Hydrolysis is the other way around.
Yep, so that looks good. And so, right, you can think about the mechanism as well, if that helps. And so part of the other trick is you're trying to figure out, right, where the bond formation is. So you can circle that maybe. There's your amide bond. And then that's kind of your hint, right? Well, they have to connect there, probably some sort of condensation reaction. So that's where you get the carboxylic acid group from. And again, you can think about mechanism, right? Nitrogen would attack. That leaves our new amide bond formation. And this proton will hitch up with our water, right, by proton transfer or deprotonation, reprotonation mechanism. Any questions about this one?
Well, specifically, I guess a little bit, what exactly would be the meaning for those monomers? If we could go over that too, because I think for me, one of the main things is the
So how would you name these?
well, I know there's two amines.
So see if you can guess your names here. So what's a possible name for this one? See where, any guesses?
I'm trying to remember what the specific name it was for like stuff that had events in it. But I think that something that you could maybe have is like a 1,3 amino benzene.
Yeah, so 1,3, we're just missing the diamino though, since there's two of them. So diaminobenzene.
I know, I thought so too.
And then you could also name it, I think the proper IUPAC name is benzene 1,3-diamine. But
Just because of the alphabetical order.
yeah,
Mm.
Yeah, so cyclohexane is just the single bonded ones.
And I know with the other one, you have two, I think, what, carboxylic acids on there, right?
Yep.
So,
So yeah, we could take the same naming, right, the 1, 3, since it's still in the 1 and 3 positions. So dicarboxylic acid benzene. Oops, benzene. Or we could have also used, so these are both meta substituted, right? So ortho, meta, para. So this could be a meta, and this is another name for it. So metaphenylene diamine. So sometimes, right, they use the phenylene or benzene as well interchangeably. Same thing, this could be, right, meta dicarboxylic acid. So a few variations for these. And then, just to be even more confusing, for some reason, all the different 1, 2, 1, 3, and 1, 4, so orthometapara positions have special names, so.
Just to make it faster. That's like trying to say, protect the plastic, the balance.
Yeah.
So that PHTH is so without.
So other things we might have to do for naming is, so I like esters, but I'll probably ask you to name the alcohol and carboxylic acid. So 1, 2, 3. So given this ester, so name the alcohol and carboxylic acid that were used to make this. Did we, well, I guess the first step is, did we at least write out the two structures physically, and then did we name them? So,
Those are correct or not.
wait, so what was your alcohol?
So I think propanol.
Propanol, or is there a better name for it?
Trying to remember, I don't know.
Because,
Oh,
yeah, because propanol, so 1, 2, 3, propanol is technically the straight chain.
okay.
And then versus, yeah, so this is isopropanol.
So when I put the iso in, what exactly, is it just because it's that different structure?
Yeah, it's the iso group. So this is iso versus straight chain, so that's,
Or I guess you could probably also name it like two, there has to be like two propanol or something, if I could remember isopropyl or propanol.
yeah.
Okay.
So 2-propanol could also work. So then, so isopropanol, 2-propanol. And then what was the carboxylic acid?
I had pentacillic acid.
I think you just named it, because it should be pentanoic
Oh,
acid.
yeah.
Yeah. Just watch the ending, but yeah, pentane's good. So make sure you count the 5 carbons, so 1, 2, 3, 4, 5 for your pentanoic acid, so that looks good. Questions on this one?
And then if we were to try to name the ester, because we didn't get the ester, trying to think of what that name would be for that.
So the ester naming, that's where we could name it by the different halves. So right, so this would be like isopropyl pentanoate for the ester.
And so ester, it was what, O-A-T-E for the end?
Yeah.
Okay.
Trying to remember, where was the naming?
It'd be like pentyl isopropanoate.
Yeah, so here I just pulled up the ester naming again so we could remember. So this one, like ethyl methanoate, so this one, or methyl, and then the methanoate. So kind of naming the two parts, or the pentyl, so this is right for the alcohol, and then the ethanoate 1, 2. So then if we go back to this one, then it would still be isopropanol and then a pentanoate. All right, let's try the last little bit. And so see if we can draw this amino acid, or at least, so see if you can draw that. And then there's also going to be like hybridization on the exam, so like some organic structure, and then just labeling those sp3, sp2, sp, which I think we remember, but we can review if we need. Like identifying like whether something's sp2, sp3, like for your nitrogens or carbons.
How many questions are actually on the test?
5 multiple choice questions. then let's see, 1, 2, 3, 4, 5 short answer questions that are 12 points each, and then 1, 2, 3, 4 that are, or 6 that are 5 points short answer. So 15 questions total. How much are they worth, or?
Yeah.
3 points each. Oh, and then I wanted to show one more thing, especially if some of you are thinking about taking OCHEM. So I brought my baby kit, and I like it because it's pretty unique. And so what makes it different is that all the carbons are already kind of all assembled, so they're already hybridized. So obviously, right, this is the sp3 hybridized carbon, and then these little flat ones are sp2. So it's a little different, but I like this kit a lot more for like OCHEM and stereochemistry, right? So it's really easy to build like ethane, and then you would do this in OCHEM and look at it all day. And so I like this kit a lot. It's just really hard to find. So I pulled it up for y'all. I could probably post a link if people are interested in buying it. Because, yeah, it's hard to buy, and I don't like it. I like it compared to all the other kits. So if you look at like other OCHEM kits, they all are terrible and suck. Because there's really only 2 other styles. So obviously the ball ones that you're familiar with, which are tedious. And then the other style, I'm trying to find it, and it's even worse. But it's like basically you take 2, I can't even find it now.
Are there those good computer programs for build volatiles? Kind of like what we did earlier in the year?
I need to find,
Yeah, there's some programs that.
yeah. I need to find which one is more user-friendly and accessible. Well, I don't know why I'm not, I was trying to pull up the other crappy kit, but.
It was so crappy, you didn't come up with any
Yeah. So I'll post a link to this one. It's a good one. Oh, I found the other terrible one. So it's not showing a good picture, but this one I've seen in like a lot of college bookstores. And I know it's a bad picture, but if you can kind of tell, what you have to do is like hook them like that, and it's really horrible and tedious, and you're like trying to press the little center together to like make a stupid molecule. It's really horrible, and you can see the kind of double bonds. I don't like this kit as much.
Sounds like there's some past issues.
I mean, when you're like on an exam trying to like stick your chiral center together, and it's yeah. As opposed to like, oh, chiral center. Like, yeah. Or just like watching students on exams, like trying to build kits with all these other ones, and you're just like, oh gosh. All right, how did our drawing go? Does someone put it on the board for us? Everyone look.
Huh?
Yeah.
I already did a problem today. I already did a problem today.
I got something, because
Yeah, go for it. You could always put on the far board too. There's more space.
Where less people will judge you.
I mean, we also plan on like erasing your stuff. I don't care about it anymore. No.
Yeah, we need to erase all the gross physics stuff now.
Hey.
So, starting off, I got this. So that's what I got for mine.
So that looks good to me. I'm just, where?
Or does it not remain at NH2 or is it?
Well, I think for the polypeptide, it's got, basically on one end it's the NH2 and then on the other is
Yeah.
OH, just so that they can combine.
Yeah. Yeah, so your first part just starts with the amine, and we don't really have it attached to anything, right? So sometimes you attach these to like beads or some sort of thing to start your amino acid if you're making it like in a lab. And then I like the way he wrote it out. So right, our amine and then carbon-carbon, and of course, right, this is your carbon with your stereo center, and then carboxylic acid carbon, and then I'm just slow to copy the R groups. 1, 2. And then I'm just switching colors too so we can see the different amino acids. And then again, amide bond formations. So nitrogen, carbon, carbon. And then, yeah, we just have our carboxylic acid group at the end. Any questions? questions on this one? Or anything else? Feeling good about everything?
Definitely needed the review. Yeah.
Yeah.
We've been doing so much OChem that that's just been on the brain. And I forget about the electrochemistry and all of that. Oh, shoot.
Yeah.
Yeah, that feels like it was wild.
It does.
Yeah.
All right, I'm going to stop our official review here.